on earth? What on? No, no, no. Can you believe this? I bought this book, What to Expect When You're Expecting. It should have been all about expected values, and it doesn't have a single mention of variance, regressions, heteroskedasticity. It's a book that promises to be about statistics, and it's got none of it in it. Just an absolute worst $18.95 I ever spent. All right, it's 5:45 on a Sunday, so it's time for a pretty quick econometrics lecture. But I'm sorry, I'm wearing a baseball cap. That's very unprofessional. Let me just uh, get situated. All right, much better. Much better. Here we go. Okay, and so this lecture is going to be quick for two reasons. Today we're talking about heteroskedasticity, covered in chapter 10 of your textbook. Reason one, it's going to be quick. This is a topic that has a pretty quick fix. So this is another OLS assumption violation. We're going to be talking about its consequences, but detecting it and correcting for it is pretty quick relative to things like functional form and omitted variables bias that take a lot more thought. The other reason this lecture might be on the quick side is, well, here's my little baby cam. Does that show up? There's Thomas. He's taking a nap right now, but so I'm trying to get this thing done before he wakes up. And so I might have 5 minutes, I might have 2.5 hours. You really can't know. All right, so let's get started. So I'm going back to kind of our handout that's been our guide for the rest of the semester. We took a slight detour when we did difference and differences last lecture. So this is a list of kind of OLS assumption violations, and when we do the appropriate lecture, I'm kind of filling in the appropriate section. So today we're going to be talking about heteroskedasticity. Heteroskedasticity actually has two kind of versions of it. There's what's called pure heteroskedasticity and impure heteroskedasticity. And so I'm quickly going to kind of fill in this sheet. This will be on Moodle. To kind of give you a sense of where the lecture is going, then we'll dive into the details. Pure heteroskedasticity is a violation of assumption 1 of no heteroskedasticity. Impure heteroskedasticity is actually a violation of assumption 5. Impure is a violation of assumption 1. That is, impure heteroskedasticity occurs when functional form is incorrect. We've got our definitions of heteroskedasticity. Heteroskedasticity has to do with the error term. It's going to be when the variance of the error term is not constant. And regardless of whether we're talking about pure or impure heteroskedasticity, the consequence of it is that it's going to bias our standard errors. In other words, our t-statistics are going to be wrong, our guesses as towards statistical significance, all of that's going to be incorrect. And, well, actually, I guess I'll come into the last two columns. How do we detect it and how do we correct for it after I kind of go through the slides and a stata example. All right, so we're going to start off today by defining pure heteroskedasticity versus impure. Then I'm going to show you how to detect heteroskedasticity. Then I'm going to show you how to correct for it, which is a very quick fix. That's the nice thing about heteroskedasticity. And then I'll show you an example in stata, and we'll come back and we'll fill out that table. So pure heteroskedasticity, normally you don't even use the word pure in front of it because it's just what heteroskedasticity is, and it happens when the variance of the error term is not constant. Yeah, I can skip that. The next two graphs, it's a little difficult sometimes to visualize heteroskedasticity, but so this kind of 3D graph, which is something much better than I could draw on a whiteboard, this is an example of homoskedastic or no heteroskedasticity. What we have here on the z-axis, kind of coming from left to right, you can think of as a z or an x variable. The y variable is on the vertical axis, and then the distribution of the error term is on the back and forth axis. Y is not in this picture. So the kind of likelihood of the error term is on the vertical axis, and then the value of the error term is on this kind of diagonal axis. Homoskedastic data, the distribution of the error term is the same regardless of where you are in the data set. Heteroskedastic data, the distribution of the error term changes depending where you are in the data set. So maybe people with smaller values of z's have more tightly distributed error terms. In other words, their error terms are much closer to 0 on average, whereas for larger values of z, the distribution or the variance in the error term has increased. So still centered around 0, you're still equally likely to have a positive or a negative error term for large values of z, but the distribution, kind of how likely you are to be really far away, has gone up. Impure heteroskedasticity, on the other hand, is heteroskedasticity that is due to incorrect functional form. That is, because you're measuring one of your variables kind of incorrectly or non-optimally, you introduce heteroskedasticity kind of where it doesn't need to be there or accidentally. An example of this is the graph below, where a better specification of this graph would have been if the, I believe if the x variable, yes, if the x variable were logged. It's pretty clear that kind of the relationship between x and y here looks something, and sorry, I don't have my mouse, so I'm using a laptop keyboard, which is always a little tricky. But there's kind of a curved relationship between x and y in this case. And when you have a relationship that looks like that, that is similar to the function y equals ln of x. And so my guess is, with this data, if you were to log the x variable, the relationship between x and y would look more linear, it would be better suited for OLS, you'd improve the model. Why does this introduce heteroskedasticity? Well, for variables towards the low end of this distribution, maybe around in this 300 to 400 point range, because the wrong functional form was chosen, you can see that the residuals vary really, really widely towards the low end of the data. So in this range, they go all the way from up here all the way down there. Whereas towards the higher end of the data, once the relationship starts to look a little more linear, if we're around 500 points or up in the 600 points, kind of the variance in the error terms is much smaller. You're not off by as far towards the higher end of the data. So this could ultimately be corrected by fixing the functional form, but still the consequence of the heteroskedasticity is going to be the same in that your standard errors are going to be biased if you estimate a model with the wrong functional form. Heteroskedasticity, importantly, does not cause bias in your coefficients. In other words, your slope estimates are okay even if you have heteroskedasticity. What it does is it causes OLS to no longer be the minimum variance estimator. It's not best anymore. And it causes the standard errors to be incorrect. Typically, it causes your standard errors to be too small. If your standard errors are too small, then your t statistics are too big, and you are too likely. You are too likely to kind of reject the null hypothesis, too likely to find statistical significance. So you're going to claim that there are kind of significant findings when actually there are not. To test for heteroskedasticity, we're going to use. Is it next? Okay. I should have, the first thing on this list should be what's called the eyeball test. That's going to be on the next slide. But to test for heteroskedasticity, we're going to talk about two ways. First is going to be the eyeball test, which is exactly what it sounds like. And then the second is the Bruce-Pagan test, which is a more formal mathematical test. And there's a third option, the white test. We're not going to talk about that this semester. The only one I expect you to kind of know or understand is the Bruce-Pagan test. So we'll talk about that in a second. Before testing, think about your functional form and look for early warning signs of heteroskedasticity. That could include really, really, really large t statistics and graphs of your data. So the eyeball test, I've shown something similar to this in class before, but the eyeball test, what you should do is you should graph your residuals. So notice that the y-axis here is the residual. So maybe after you run a regression, you can then create a variable that is your residuals, how far off your model is from the actual y variable, and you can plot those residuals against an x variable or a z variable on the x-axis to kind of look at, does it seem to be that the variance in my residuals changes as I go along the data, in some range of the data. In this case, these are kind of stylized graphs, but both cases, there would this would look like heteroskedastic data. The variance on the top graph of the residuals is much larger out towards the right. On the bottom graph, the variance of the residuals is much larger towards the left. It doesn't need to be kind of a monotonic or constantly increasing or decreasing. This is another example that would also be heteroskedastic. In this case, the high variance is kind of in this middle range of the data. And then there's lower variance, so high variance in this middle range, and lower variance on kind of either end. That's still heteroskedasticity. That is still a case where the residuals or the error terms have different variance at some part of the data than others. So how can we kind of test for this formally? The eyeball test is great in stylized graphs like that. Often we might have scatter plots with thousands of data points, or where it's a grayer area, it's not totally obvious. So how can we test for it? The answer is the Bruch-Pagan test, which is kind of a clever way of using regressions. So we know that after we run a regression, we can calculate the residual by subtracting the actual value in our data from the predicted value. Now, if we have heteroskedasticity in our data, that you can think of that as sort of saying that the x variable, or an x variable, or a z variable, I'm not sure why these slides use z. I would usually use x, but that an x variable is correlated with the variance of the residual. Now, if we were to look at kind of the linear relationship between this z variable and this residual, it would probably be pretty close to a flat straight line. And that's because residuals are equally likely to be above or below zero. What the Bruch-Pagan test does is it generates the square of the residual. So now everything's going to be positive because it's squared, but importantly, large values of residuals, regardless of whether they are large positive or large negative values, are now going to be really, really big. And smaller values are going to be closer to zero. What the Bruch-Pagan test does is it looks at whether the x variables in your model are correlated with the square of the residuals. In other words, is there some variable that can predict whether your residuals are large or small? And if there is, then that's an indication that there is heteroskedasticity in your data. If there's an x variable that can reliably, statistically significantly predict when your residuals are big or small, then that means that at some points in your data, you have higher variance than others. The way that we formally test this is very similar to the F-test. Technically speaking, it's what's called a chi-squared test. I'm going to show you how you do that in Stata in a minute, so don't sweat it too much. An example using kind of the restaurant example that we've used all semester. So we're predicting a restaurant sales based on the number of competing restaurants, the population, and the income of that population. The auxiliary regression, we run that regression, we generate residuals. The auxiliary regression, the regression that's going to do the Bruch-Pagan test, then puts number of competing restaurants, population, and income of the area as the explanatory variables for the residual squared. In this auxiliary regression, these variables only predict 0.044% of the residual, so there's not a super strong correlation. And our chi-squared statistic is 1.4, whereas our critical value of the chi-squared statistic is 7.8. In typical fashion, we're going to see an example of this in just a second, but in typical fashion, if your test value is below the critical value, you fail to reject the null. So this would be a situation, at least with Woody's Restaurants, that we can't reject the null hypothesis, which would mean we are not sure that there is heteroskedasticity. The heteroskedasticity test is a case where kind of if you think heteroskedasticity is a bad thing, then you don't want to be rejecting the null. The null hypothesis in this case is homoskedasticity. The alternative is heteroskedasticity. If you fail to reject the null, that means you're kind of saying we can't rule out that my data is homoskedastic, that it conforms to the typical OLS assumptions. All right, well, let's go to Stata quickly now to kind of see an example of the Bruch-Pagan test and how to check it against the critical value. The command that you're going to be using, this is regardless of how many variables you have, what things look like, the command is always the same. Estat het test, comma, right-hand side, or RHS. Estat stands for estimate a statistic. You run this command after running your regression. After you run your regression, Stata lets you do a lot of things. One of them is predict residuals or predict your Y variables. This is another thing. So it says calculate, after you run a regression, calculate a statistic. I want you to do the heteroskedasticity test. And then there's a few different heteroskedasticity tests. And so Stata's kind of code for the Bruce-Pagan test is called the RHS, which stands for right-hand side. In other words, we're using the variables that are on the right-hand side of our equation to test for heteroskedasticity. I know it feels kind of weird why things are named what they are in Stata, but that's how we get there. All right, so I'm going to pull open data and let's see, slide that over there. All right, and uh-oh, my data set is not found. So let me, what's going on here? I will, sorry, this is probably going to be a 10 or 20 second pause. All right, here we go. Sorry about that. So, this is actually a data set. I now forget whether I used it on your guys's midterm or the midterm this semester before, but it's a data set about speeding tickets and trying to predict the price of a speeding ticket. I went ahead, the data set's really, really big. It's like 3,600 observations, so I went ahead and kind of just randomly kept 1% of the data set. So we're now down to 687 observations. And the reason for that is just so in this example, things don't take quite so long to run, and the scatter plots will be a little clearer when there aren't 3,600 dots onto them. Okay, so in this data set, we have what we want to predict is the amount of a speeding ticket fine. So our outcome variable is going to be the amount, and the two things we're going to use to predict how much people get charged for a speeding ticket are MPH over. That's how far over the speed limit they were when they got pulled over for the ticket, and female, whether or not the person receiving the ticket was male or female. So if we do this using, so first, no, let's do the regression first. Regress amount, MPH over, and female. And so we have here, unsurprisingly, that the amount over the speed limit you were is highly, highly statistically significantly correlated with whether or not, with the amount that you pay. Whereas the gender is marginally significant, but we would not reject this null hypothesis at the 5% level, even though we would reject it at the 10% level. Or I guess that's using a two-sided test. So we would, on a one-sided test, we would reject at the 5% level too. So it's kind of just barely significant. We can then, in Stata, we can type predict, let's call them amount residuals. And so now, in my table of data, here's my data set. I just generated a new variable that is the residual from that regression. Certain observations weren't included because the amount of the speeding ticket was not always known. And so let's take a look at resid amount and MPH over. So first we're going to do the eyeball test. Does it look like there's heteroskedasticity in this data? Certainly looks like it to me. It looks like the story here is that for people who are maybe 8 or 9 miles per hour over, first of all, there's one poor person who got pulled over when they were like 3 miles per hour over the speed limit. So that's some jerk of a cop. But when people are like 8, 9, 10 miles an hour over the speed limit, our model does pretty well. It's usually predicting the price of the ticket within like $20 or $50. However, when some people are 20 or 30 miles over the speed limit, the variance in the amount of their ticket goes way, way up. So this is kind of clear eyeball evidence of heteroskedasticity. I'd be super surprised if when we do the formal test, we don't find heteroskedasticity in this case. And in this particular example, it makes sense. There's going to be some cases, the lucky guy all the way down here, probably a case of someone got pulled over going 30 miles over the speed limit, but managed to either sweet talk the cop or somehow get out of the ticket. And so the model predicts they should be paying $300 or $150, and actually they pay nothing. All right, so we're going to do our formal test, estat at test, right-hand side. That's going to do the Bruce-Pagan test. And so we do this test, and we interpreted this like we'd interpret lots of tests before in this class. It's a chi-squared test, and so we get a chi-squared value of 156, and then we get a p-value for that test. And this p-value is 0, which means there's a 0.000 chance that we're making a type 1 error. This is clear evidence of rejecting the null hypothesis. If I want to make this a little more formal, though, what do I compare this number 156.8 to? On Moodle, let's see. On Moodle, in the stats and math review section of Moodle, there's a PDF called Other Tables. This is where the chi-squared table lives. The reason it's there is because we're honestly not using it that much. Most of the time when you're doing the heteroskedasticity test, you can just use the p-value. If this p-value is less than 0.05, you reject the null hypothesis and you claim that there is heteroskedasticity in your data. Got to stop the annotation. So in this file on Moodle, here's the chi-squared distribution that gives you the critical value based on your degrees of freedom. In this case, your degrees of freedom is k, the number of explanatory variables in your model. That's why this table doesn't go up too high, because you rarely have more than, rarely have more than 10, let alone 20 explanatory variables. But so in the last model I just did, I had 2 explanatory variables. At the 5% level, our critical value is 5.99. 156.88 is clearly bigger than 5.99, so we reject the null hypothesis. Okay, so now going back to our study guide, we're filling in the detection column. How do you detect pure heteroskedasticity? The eyeball test, the Bruce-Pagan test, or theory. For impure heteroskedasticity, we kind of use the same criteria. Bruce-Pagan test, theory, but the theory we're relying on for impure heteroskedasticity would kind of be about the functional form. Rather than something that just tells us, oh, these people should be higher variance than these other people, to detect impure heteroskedasticity, you might have a theory that your functional form is wrong or could be improved. So now to wrap up the lecture, we need to talk about how to correct for heteroskedasticity. We got to fill in this last column. And sorry that this functional form column was kind of filled in through this whole thing. I guess I could just... There we go. Now we can kind of see everything on the same page. All right. So back to our slides. To correct for heteroskedasticity, so the first thing is to look at your functional form. If it's impure heteroskedasticity, the best way to correct it is fixing the functional form. If there's no obvious specification errors, then we go on to our quick fix, which is called heteroskedastic corrected standard errors. These are typically, they're not minimum variance. So when we use these, our model is not as precise as possible, but they tend to be more accurate at estimating standard errors under heteroskedasticity. And they can still be used with the standard t-test that we always use to use hypothesis testing. And to implement them, It's as simple as typing the word robust after you run your regression. So here's kind of an example below: regress sales on competition income, comma, robust. Economists, this option on a regression is so famous that often economists will just say, oh yeah, I'm using comma robust standard errors. And everyone knows what they mean because typing comma robust is just used so pervasively in economics. Let's see an example of that in Stata first. So we're back at our speeding ticket data set. So we've confirmed that there is heteroskedasticity both from the eyeball test and from the Bruce-Pagan test. Now I'm just going to write comma robust. And so what I'm expecting to see here is that there was clear evidence of heteroskedasticity in the miles per hour variable. I'm expecting this t statistic to go down. In other words, I'm sure miles per hour over the speed limit is still statistically significant. I would be very surprised if it were not significant after using robust standard errors, but in all likelihood, we were overstating the statistical significance in the original regression. So let's go ahead and run this. And sure enough, the t-stats have dropped by about 30%, down to 13.9. Still highly statistically significant, but not quite as high of a t-score. The coefficient, or the t-statistic on the female coefficient, is negative 1.74. Compare that to negative 1.75. That's evidence that there probably is not heteroskedasticity when it comes to the female variable. In other words, the variance of speeding ticket amounts is similar for men and women. All right, so for fixing heteroskedasticity, you can redefine variables. That's kind of fixing your functional form. You can use the robust test. The other thing to think about is sometimes is maybe adding an extra variable. This example shows how maybe if you don't have a dummy variable, for example, for large cities in this stylized example, you could kind of be estimating the wrong slope. So, and thus introducing heteroskedasticity. This lower dotted line fits the small cities data, this cluster of small cities data, pretty well. Whereas if you do include the large cities, the slope of the line then goes up to this steeper slope line, which, yes, it fits the large cities, but it introduces heteroskedasticity because then in Stata's mind, or in the regression's mind, for larger cities, some of them have really small residuals, whereas some of them have much larger residuals. A smarter thing to do here might be to include a dummy variable for whether the city is large or small and kind of account for the fact that larger cities have this huge increase, in this case, in expenditures. So that might be how fixing functional form can help correct for heteroskedasticity a little bit. All right, so that's the end of the slides. And let's finish off by completing our table, that the way we correct for pure heteroskedasticity is by estimating robust standard errors. The way we correct for impure heteroskedasticity is by fixing the functional form. And there you have it. A pretty quick rundown of heteroskedasticity. I think that'll be the last time today I have to say that word. Look for a lecture on multicollinearity next, which is also a relatively quick fix. In your final projects, I'm expecting you to test your main regression for heteroskedasticity. If you have evidence of it, I'd like to see you fix it. And if you don't, then you don't need to do anything. So that's it for this lecture. See you guys later this week.